Welcome to the session, everyone. I'm Dr. Aris. Today, we are going to explore the very fabric of our reality through the Standard Model, which serves as the universe's ultimate blueprint. Think of it as the fundamental source code for the cosmos. This model is a sophisticated theoretical map. It identifies the most basic building blocks of the universe and explains the beautiful symmetry behind how they interact through physical laws. Take a look at this organizational structure. As we progress, NOVA will help us visualize these abstract particles with data-driven simulations to bridge the gap between complex theory and experimental observation. Our first major category consists of fermions. These are the matter particles that provide the substance of our physical world, acting as the bricks of everything we see and touch. Finally, we have bosons, the force carriers, and the Higgs boson, which grants particles their mass. Sophie, I know you're keen to discuss the mathematical elegance of the Higgs field later. Let's start our journey by looking at quarks. Continuing from our introduction to the Standard Model, let's dive into quarks. These are the truly fundamental building blocks of hadrons, the particles that make up the atomic nucleus. We have 6 distinct flavors of quarks. The up, charm, and top quarks form the first group. What's fascinating is that they each carry a fractional electric charge of positive 2/3. The other 3 are the down, strange, and bottom quarks. These carry a negative 1/3 charge. This fractional nature was a groundbreaking discovery. As we previously thought, charge only came in whole units. Leo, look at how these combine to form the matter we know. A proton is made of 2 ups and 1 down. If you sum those charges, plus 4/3 minus 1/3, you get exactly plus 1. Similarly, a neutron consists of 1 up and 2 downs, which sums perfectly to 0. Sophie, this mathematical balance is why the neutron is electrically neutral. Now, let's move on to the particles that prefer to stay solitary, the leptons. Unlike the quarks we just covered, which are perpetually bound inside larger particles, leptons are the true loners of the subatomic world. They are fundamental particles that do not experience the strong nuclear force, which allows them to exist independently in the universe. In the first generation, we find the most familiar lepton, the electron. It is the architect of chemistry and electricity. However, it has a ghostly partner called the electron neutrino, which is nearly massless and incredibly difficult to detect. As we move into the second and third generations, we encounter the muon and the tau. You can think of these as the electron's heavier, more exotic cousins. They are unstable and decay quickly, but they follow the same structural pattern, each having its own specific neutrino partner. Notice the mathematical elegance in their properties. The charged leptons, the electron, muon, and tau, all carry a charge of exactly -1. Their neutrino counterparts, on the other hand, are electrically neutral. This neutrality is why billions of neutrinos are passing through you right now without leaving a trace. Welcome to the subatomic world. This 3D visualization allows us to explore the fundamental building blocks of the universe. Let's start by looking at the quarks. These are the particles that combine to form protons and neutrons. This is the up quark. In this view, the size of the sphere represents its relative mass compared to other particles. You can use this slider to adjust the rotation speed of the grid, helping you view the particles from different angles. Now, let's shift our focus to the bosons, which are the force-carrying particles of the Standard Model. The Higgs boson is unique because it is associated with the field that gives mass to other fundamental particles. Try clicking on any individual particle to see its specific properties like electric charge and spin. Now that we've explored the building blocks of matter, the fermions, we need to understand the glue that holds the universe together. These are the gauge bosons, the fundamental force carriers of the Standard Model. First, we have the photon. This is the mediator of the electromagnetic force. Because it is massless, it has an infinite range, allowing it to carry everything from the light of distant stars to the signals in your smartphone. Next is the gluon. As the name suggests, it acts as the glue that binds quarks together to form protons and neutrons. It mediates the strong nuclear force, which is the most powerful force in nature, though it only acts over incredibly tiny distances. Finally, we look at the W and Z bosons. Unlike the others, these particles are quite heavy. They mediate the weak nuclear force, which is responsible for certain types of radioactive decay and is a key player in the fusion processes that keep our sun burning. To visualize how these particles actually exchange forces, let's watch this simulation showing the interaction between matter particles and their force carriers.
The exchange of virtual bosons mediates the realm be attractive or repulsive, depending on the charges of the particle.
It's fascinating to see how these exchanges happen almost instantaneously. Leo, you've always been curious about the missing pieces of the standard model looking at these four carriers. Does anything stand out to you about the forces we haven't mentioned yet? Now that we've seen how forces are carried by gauge bosons, we encounter a fundamental problem. Why do some of those particles have mass while others, like the photon, have none? This leads us to the most famous piece of the puzzle, the Higgs boson and the origin of mass. For decades, this was just a theoretical prediction. But in 2012, the scientific world reached a milestone when researchers at CERN's Large Hadron Collider finally confirmed its existence, providing the experimental proof we needed to validate the standard model. The particle itself is actually a ripple in what we call the Higgs field. Unlike other fields, this is an invisible energy field that permeates every single corner of space-time, even in a total vacuum. So, how does it give mass? Imagine the field as a thick syrup. As particles move through it, they interact with the field and experience a kind of drag. The more a particle sticks to this field, the more mass it gains. Without this interaction, everything would zip around at the speed of light. Mathematically, this is represented by the Higgs potential formula you see here. In physics, we often visualize this as the Mexican hat model, which illustrates how the field settles into a state that allows particles to acquire mass through a process called spontaneous symmetry breaking. Building on what we just covered regarding the Higgs field and mass, we now need to see how these particles actually communicate with each other through forces. This is where the standard model shows its incredible predictive power and its frustrating limits. Take a look at this summary table. We've talked about the strong force mediated by gluons and the weak force involving the W and Z bosons. Each of these forces has a specific range and a specific carrier that allows particles to interact. Note how the electromagnetic force carried by the photon has an infinite range, whereas the nuclear forces are confined to almost unimaginably small distances. Notice that the strong force is significantly more powerful than the others at these scales, which is exactly why it can hold the nucleus together despite the electromagnetic repulsion between protons. However, as complete as this looks, physicists are very aware of the missing pieces. The standard model is essentially a blueprint that leaves out the most famous force in the universe. That missing piece is gravity. It isn't described by the standard model framework at all. We haven't confirmed a graviton particle, and our current math for quantum mechanics doesn't easily align with Einstein's general relativity. Leo, I know you're always thinking about the bigger picture of the particle zoo and what lies beyond. Now that we've explored the fundamental forces and the mysteries of the Higgs field, it's time to put your knowledge to the test in our final project, the Particle Identification Challenge. We have simulated data from a high-energy collider experiment, and your mission is to identify whether these detection events represent known standard model particles or perhaps something even more exotic. You'll need to carefully analyze decay paths and apply the conservation laws like charge and spin that we've covered throughout this session to deduce the identity of our mystery particles. Nova is ready to provide the data-driven summaries from the digital lab, so please select your roles and let's begin the investigation. Wonderful job on those identification challenges, everyone. To conclude our session today, let's synthesize everything we've learned and peer into the future of particle physics. We've spent today dissecting the core framework. As we discussed when exploring the particle zoo on page 4, this model represents our most comprehensive map of the subatomic world. It provides a unified description of quarks, leptons, and the gauge bosons that carry the fundamental forces, all tied together by the Higgs mechanism we covered earlier. But science is never truly finished. We are now looking toward future frontiers where the standard model alone cannot explain the mysteries of the cosmos. Current experiments at the LHC and beyond are hunting for the nature of dark matter and trying to understand the matter-antimatter asymmetry. These are the puzzles that the next generation of physicists, perhaps some of you, will solve. By seeking these fundamental symmetries, we get closer to a truly complete theory of everything. Thank you for your incredible focus and curiosity throughout this session. It has been a pleasure exploring the building blocks of the universe with you.